He is a man of virtue and simplicity. I am elated. After all, he is a living inspiration for the young faculty members and research scholars. Ajeet Kumar was born in 1983 in India. He received the BSc degree from Deen Dayal Upadhyay Gorakhpur University, Gorakhpur, India in 2002. The MSc degree from the Indian Institute of Technology, Roorkee, Roorkee, India in 2004, and the PhD degree from the Indian Institute of Technology, Roorkee, Roorkee, India in 2009. He was a postdoctoral fellow in the Gwangju Institute of Science and Technology, GIST, Korea. In July 2010, he joined the Delhi Technological University, Delhi, where he is currently an assistant professor. He has published more than 100 research articles in journals and conferences. His current research interest includes large mode area, single mode fibers, segmented cladding fibers, fiber optic sensors, and waveguide long period gratings. Dr. Kumar has recipient of Young Scientist Award by Uttarakhand Government, India. He is a life member of Optical Society of India, OSI, Optical Laser Association, ILA, and the Indian Science Congress Association, ISCA, and also the member of Optical Society of America, OSA. I am not taking so many time in between him and all of you. Please welcome Dr. Ajeet Kumar sir.
Thank you, sir. Am I audible?
Yes, sir. Yes, sir. You are audible, and your presentation is also visible.
Okay.
Slight gray color patch is coming. I think you need to minimize that window on your screen. Top corner. Sir, please.
Good afternoon, one and everyone present here. And before I'll start the talk, let me thank you, the organizers for inviting me to present my work and have the interaction with all the, especially the faculty members and research students, and discuss my ideas, the kind of work we are doing from last few years. It's a kind of exchange of the ideas during this 1 week online faculty developed program on photonics, active learning in optics and photonics, which is sponsored by the AICT training and learning program. During my talk, basically, I'm going to discuss about the kind of work we have done in order to modify the design of the host material, which is a waveguide or fiber, which is a very important parameter in order to increase the power level of the high power waveguide and lasers. We'll discuss in detail, and you will see that there are a number of parameters. There are basically a number of parameters which is actually addressing in order to increase the power level, which is of any designed fiber or waveguide lasers. But discuss about the host, which is a very important one. And before I'll proceed for my talk, I'll just in order to give the why this the particular topic is so important. I would just like to mention that I'm basically in one of the member of as a outside expert of the committee which is there in the DRDO, and the DRDO basically the government of India from last 5-6 years, their motive is basically to come up with some indigenous technology developed at the DRDO lab in order to increase the high power fiber lasers of the so what they have done initially, the one of the group, I cannot share the details because the DRDO it's a kind of secrecy is there, but some of the things which I can discuss before the presentation, I just like to mention that there are two different groups over there. One of group is working on the CW laser, one of the group is working on the spun laser, and their motto is to develop the high power fiber lasers at the kilowatt range. So initially what the government has done, they have a collaboration with the Israel group, and the DRDO, one of the lab has developed the the high power fiber laser with the help of the Israeli group, and then after that they have given a task to the DRDO. You have to develop level at the in DRDO less technology. So because of this the importance of this high power fiber lasers, no from last 5-6 years the government is giving so much emphasis, and in order to develop this kind of high power fiber lasers in 2 different groups at DRDO. So this basically you simply says you the importance of the high power fiber lasers. I'm not the experimentalist. I'm basically doing the simulations, but being being in touch with the such great scientists working over there, even what I have realized, doing the things at experimental level and the theoretical level are quite far apart. But at the same time, you will see the challenges, and number of the times you encounter the challenges there, which is there in the case of experiments with the help of the theory. So there are 2 aspects from the beginning in case of physics. Either in some cases first theory comes, then which is the followed by the experiment. In some cases experiments comes, which is followed by the theory. So in order to have the better understanding, you should, even you are a theoretician, you should know the feature of the experimentalist. You should know what is their fabrication limit, and even if you are a experimentalist, you should know the basic principle and ideas about the theory. Then you can progress and you can enjoy the things. So the topic of my presentation is design and analysis of specialty optical fibers and waveguides for the high power fiber laser. So I'll start with the presentation with a very interesting topic like light matter interaction, and I think most of the audience are the faculty members and the PhD students, and all from the BSc and master's standards. If we read number of effects, we read about the photoelectric Compton pair effect, the pair productions, and if in the advanced stage, if you come to the MSc levels, you know about something called if you are working the domain of fiber of the photonics, you read about the supercontinuum generation, the frequency generations, like the self-focusing kind of phenomena. So all these phenomena are all together, if you see, it is nothing but it is basically the light matter interaction. What is important in the case of the physics is the condition. What I realize, it is the condition which basically gives you the different output. Like if you talk about the light matter interaction, we know that in one case we will get the photoelectric effect, in which we see the the emission of the photoelectrons, and if in another case we will see the Compton effect, where we'll see that if the light is interacting with the matter, you are basically and the of the light is input, you will as well as will get also delta lambda. So you will basically instead of lambda, you also get lambda prime, lambda dash. So this effect is called Compton effect. The third point is called the pair productions, in which when the light is interacting with the matter, you are basically getting the the two antiparticles. Why these? And all these are basically light matter interaction. Only the difference is in case of the photoelectric effect, the energy of the light will be low. In the case of the Compton effect, the energy of the light will be in the medium range, and in case of the pair production, the light energy will be very high. So just by changing the condition, which is the energy of the incident radiation, you'll see different effects. And one of the beautiful things about this pair production is this basically gives you the existence of the the particles, the existence of the antiparticle. And the beautiful thing about this, when I read about the the history of this pair production, then I came to know that the Dirac has given an idea of the relativistic quantum mechanics. I think everybody have gone through it, and he said that there is a concept of antiparticle or antimatter. The moment he has given, I exactly don't remember the year, but the year he has given this idea, it was a completely theoretical idea. He has done the relativistic calculation of the quantum mechanical particle, Dirac's, and finally he has given that there is existence of antiparticle. And just after 4 years, there was a scientist, the Anderson, he was performing the experiment on the, on the cosmic rays. He was not working on the pair production. He was just trying to study the effect of a cosmic rays. And in order to do that, what he did basically, he created that kind of chamber, and in that particular chamber he applied the magnetic field, and then he has assigned this field with the very highly energetic cosmic ray, and then he performed the experiment and then see this kind of behavior like that. And when he has calculated the mass of this one particle, it is same as electron, and this one is also same as electron, but the path was different. So what is concluded, one is electron and one is the positron, antiparticle. So just after 5 years of the of the theory, this theory was backed by the experiment of the pair production. So this is one thing about the light matter interaction. Now come to the another point. Again, if the light is going to interact with the matter under again spatial condition, that spatial condition is called, say, stimulated emission. Under that condition, you will get a new light, or a light with some spatial feature, which is called laser. And this light with the spatial feature causes new things, because this one of the spatial feature of the laser is it is a very highly power. It is basically highly monochromatic, and the power is very high. It is highly coherent, and in that case, these are some features which makes this light different from this light. So the light matter interaction is giving you new light, a light with some spatial feature. Now this has opened the new field. When this new light is going to interact with again with the matter, okay, which is having some spatial feature, you will see very new phenomena which is not there in the light matter interaction before the invention of the laser. So even if you want to categorize the time, all the experiments at the time, you can categorize them before the invention of the laser and after the invention of the laser. After the invention of the laser, you have a light source, which is a very coherent source, high power source, highly monochromatic source, and that is going to interact with the medium. And in that case, you will see that even the induced polarization, which you usually say in case of linear optics, the induced polarization P is only proportional to here in incident electric field E. But here we basically drop the all higher order term. But here in case of this particular case, we cannot simply write this P is proportional to E. We have to include all some other higher order terms like this. So this is called nonlinear optics. And since we are including some higher order terms, this basically gives you some new features. And what are those new features? If you just like to see the new features, one of the feature is the refractive index of the medium is not constant. Refractive index of the medium is not constant, which is here in case of light matter interaction. Okay, we always say the light is interacting with the matter, the refractive index of the medium remains same. But here in this spatial case, you will see that in some of the cases, refractive index of the medium will not remain same. The second thing, if you talk about, you will see that in the linear case, if the omega frequency is propagating here, incident frequency is omega, in the output you also get the omega 1. If the incident frequency is omega 1 and omega 2, in the output you will get omega 1 and omega 2. However, in this particular case, the another difference, if the input frequency is omega 1, omega 2, there is a possibility that in output you will get omega 1, you will get omega 2. But apart from that, you will get omega 1 plus omega 2, you will also get omega 1 minus omega 2. The third difference, you will even see that here the phase cannot be changed by the phase of the light cannot be changed by the matter, but here even the phase of the light can be modulated by the matter, which is having huge applications. Okay, so even there is a possibility that because of this phenomena, you can see the matter itself can behave like a lens, and the focal length of the lens, the focal of which the of the incident light. And why these spatial features are coming? Why these spatial features are coming? These spatial features are coming because of the laser, and this laser is because of a special condition which is called stimulated emission. Before I proceed to the next slide, I will like to mention the another very beautiful the difference or the point in case of the non-linear optics is in the case of non-linear optics, what you can do in a certain conditions. And whatever the phenomena I'm mentioning here, this all phenomena again needs some certain condition. I'm not going detail into that, but what you can do, you can incident a very giant pulse of highly monochromatic giant pulse. You send that giant pulse to a matter, and in the output you can get a broadened light. So here we have a lambda, here you have a range of lambda, and this is called super continuum generation. So all this is because you have considered a light matter interaction under a certain condition, and that has actually given you the laser. Now, when we are coming to the laser, all of us know, even from the graduations, maybe even the 12th standard, we read about the lasers. The full form of the lasers is the light amplification by stimulated emission of radiation. But I just like to mention that laser is not actually the amplifier, it is basically an oscillator. That we'll discuss in the next slide. So, but the very important point about this laser is the idea, again, in the case of the laser, the idea was given by the great scientist Albert Einstein way back in 1917. Way back in 1917, he has given an idea that if the light is going to interact with the matter, he said if there is a light and that light is going to interact with the matter, what we usually see, if this is a transparent medium and light is going to interact with the medium, okay, because of the certain things, here will be your absorption, you have absorption and you have scattering, and this absorbing all this absorption and scattering, what it will do, it will basically create a loss, and because of that, in the output, whatever the the power you'll get, whatever the intensity you'll get, that will be this P2 will be always smaller than P1 because of these kind of losses. What idea is given, okay, this is the normal case, but if again the light is going to interact with the same medium under a spatial condition which is called stimulated emission. So if you have stimulated emission kind of thing, okay, then under that condition, what you can see, the light is something like this. Here in the input range, in the output you'll get the amplified light. This was the idea given by Albert Einstein in 1917, and he said that if this kind of thing will be there, you'll be able to get a new light, or the light with the new features like having very high intensity and power and highly monochromatic, having low divergence and very high degree of the coherence. So the idea of the laser, the idea of the light emission comes from the emissions and absorptions. And here I will discuss about the various phenomena, and in between I will discuss about the stimulated emission. So we know that for this process, light emission, the light matter interaction, two things you need. One is the incident light, and second thing is the medium. Okay, and if you are looking for any medium, maybe it's a lossy medium, gain medium, whatever it is, so the medium always provide you the energy levels. Okay, that we already know from the basic understanding. It is having the different allowed energy states, and the lowest energy allowed energy states the ground state, and then we have excited state. If a right photon comes and basically interact with this matter, and the energy of this photon is same as the energy difference of this particular energy level, then photon in the ground state, this can actually absorb the energy and it can go to the excited state. This phenomena is called stimulated absorption, well-known phenomena. But the nature, the nature of the atom is that it will not going to stay in the excited state for the long time. Usually the the lifetime of the excited state is basically is the order of 10 raised to power 8 and 10 raised to power 9 seconds. So very small time. So after this small time, unless until it is a special state which is called metastable state, which is actually another condition. There are so many conditions, uh, uh, which is another condition to which is required for the laser action. So we are not going into detail for that particular part right now. But if there is the atom which is there is in the excited state, now it can come down to the lower state by, of course, releasing this much energy, which is the difference of E2 minus E1. If this energy level is E1 and this energy level is E2, the atom of the excited it can come down to the ground state by two processes. One of the processes, it directly release this much energy, which is E2 minus E1. No, this is H. This much energy release, and it release this much energy and then come down to the ground state. And this phenomena is called spontaneous emission. Usually we say that whenever we discuss after doing all the calculation, we say that spontaneous emission is going to is responsible for the broadening, and because of this the light is not very highly monochromatic and things like that. But I'll like to mention that spontaneous emission is a very, very, very important emission. Laser action will never be possible. Any laser action will never be possible if you don't have the spontaneous emission. It will come to the moment when we'll discuss about the stimulated emission. So one process is it can directly come down by releasing this much energy to the ground state. This one is called spontaneous emission. Then there is another emission which is mentioned by the Einstein, that what you can do if there is an emission in the presence of a photon which is having the same energy difference, means this photon triggers this particular atom for the process of the emission. This is called stimulated, forced, okay, stimulated emission. In that case, the incident photon and your the photon which is coming because of this stimulated emission, they will be in the same phase, and since they are in the same phase, they will give you some better the light with some unique features. So one thing and see, we are getting two photons because I've just taken the example of one atom and things like that. You will get number of the photons, and since you don't want simply a light amplification, you are looking for basically the sustainable light. So what you do, you basically make use of resonator, which I'll discuss in the next slide in detail, and you get a laser light which is same in the phase, coherent light. But just see from this point only, this stimulated emission is never possible if you don't have any photon of this much energy. Okay, we know about the 3-level laser and 4-level lasers. Okay, we talk about the 3-level lasers. Just make a diagram of 3-level lasers. See here, what we do. Basically, we say that we have a pump, and by using the pump, sending the atom of this excited state, something like this. Okay, and from there, just I'm taking the example of 3-level laser, not 4-level laser, and there will be some non-radiative transitions, and this is a metastable state. I mean, the lifetime is say the order of -4 or -5 seconds, this much seconds. So there will be population inversion, and between this level there will be laser action. But the question is, in order to start the because if there are more number of atoms in the excited state, there are two possibilities. One is the spontaneous emission, another one is stimulated emission. But in stimulated emission, you need a right photon, and that right photon will come from where? It will not come from the pump. It will not. It is never. It is going to come from the pump. It will come from the spontaneous emitted photon. A number of atoms will be here. Some of them will follow the process of spontaneous emission, and that emitted photon will actually trigger the photon for the stimulated emission. So of course, in order to get the better characteristics of the laser, we try that the spontaneous emission should not be too much. But of course, in order to start the laser action, you always need a spontaneous emission. Now, what are the main components for any laser action? Just we have seen that what you always need a gain medium. A medium which can provide you the energy levels. A medium in which actually can provide you the energy level, these energy levels. So these energy levels will be provided by the gain medium. So first component for any laser you need is a gain medium. The second one, you want a pumping source which can actually send the atoms from the lower energy to excited energy states. Okay, and once the emission will takes place, something, the emitted photon, the coherent photon will come. So what you want a threshold power. So what you don't want simply amplification, you want the amplification should be for the long time. So you convert this amplifier into oscillator. You want to convert the amplifier into oscillator, and basic knowledge we know that any amplifier can be converted into a oscillator by giving a feedback, and that feedback is given by the resonator. So for any laser, you always need three things: gain medium, pumping source, and resonator. Now the resonator also decide what is the threshold power should come out, and because of that, most of the time we will say that whenever read about any laser, we say that one is fully silvered and one is partially silvered. That partially silvered will decide the threshold power. Okay, because the photon will come. Okay, it will reflect back. Again, it will go back. It will again go through the gain medium, and again it will come here. Again, it will reflect it back. So unless and until the power will go up to a certain level, this will not come out of this. So this is very much important. Even in order to make the laser is very sustainable laser, there are so many other conditions are required that we'll not discuss in detail here. So the one thing we discuss about the lasers, and the idea was what are to make the laser design. Now, just in a brief, the idea was given in 1917, but the first laser was invented is a ruby laser that we all know, and it is invented by the T.H. Menon in 1960. So idea is given by in 1970, and the first experimental working laser was invented in 1960, and that was basically a ruby laser, in which he has taken a ruby rod as a gain medium, and both the ends of that he has polished, and what was the fully and one was the transparent, just to make a resonator. And for the pumping, he needs a helical flash lamp. So all the three components has been used, and this was basically a pulsed laser, not a continuous wave laser. It was a pulsed laser, low power laser at that time, but this was a major breakthrough. This was basically a major breakthrough in the field of the photonics. Okay, I read somewhere, maybe the professor, I think the book written by Professor Ghatar, what he mentioned that the two major inventions of the 19th century, one is the laser and second one is the fiber. These laser and fiber has changed our life tremendously, and most of, I think all of us, because and their faculties, they can appreciate this. They have seen in their lifetime only. Earlier we have the telephones, and now how the mobiles comes, and now today's we are just transferring the video by using this platform. So without having any interruptions. So this has come because of the two things. One is the lasers, and second one is the fiber. So even in the case of the laser, we are talking about a semiconductor laser or any laser, but the invention starts from the first major breakthrough of the invention of the ruby laser. Yes. Any question? Hello.
Please continue. Sir, please continue.
Okay. I thought is any question. Okay. So. So this was the invention of the ruby laser, and this invention of the ruby laser has given motivated the scientists to come up with the new lasers by taking the different gain medium like solid, gas, and liquids, and try to increase the power level. So just to summarize the laser development, I have quoted this. You see, different mediums has been used, and in this different medium, you have different kind of lasers at working at a different particular wavelengths, and they are having the variety of applications. Some of them is having the industrial application, medical applications, and of course the lab application we are having. But out of this, I think I will like to address about this carbon dioxide laser, because the carbon dioxide laser is the one of the highest power level, laser available in the market. And I like to mention about this because the invention of this laser is made by the scientist born in India, and his name is Professor C.K.N. Patel. I will recommend you, if you have not gone through about his life, I'll just tell you that you should read about his life, and that will really motivate you. And you know, uh, so uh, this carbon dioxide laser was invented by the Indian-born scientist. Of course, he has invented this when he was working in the Bell Lab, and and in the Bell Lab, he did his BE from the some any government engineering college of university, which was university affiliated to the University of the Pune, and then he moved for the MS and PhD program in the US, and after doing his PhD, working with the Bell Lab, he has invented this laser. So whenever I give any talk or I'm having any interaction with my students, I always convey this about this the carbon dioxide laser, because this was invented by the Indian-born scientist, and he is still alive. He is company and working on the high power fiber lasers. Okay, so this about the summary, one of the summary of the laser you can see. But you see that having all the advantages and having variety of the applications, there is something which is need to be addressed in case of the high power fiber laser. One is the thermal management and its size. If you want to use your fiber for certain applications where you want to carry your you want to carry your fiber lasers very frequently, or you want to make a very compact kind of fiber system because of your need, in that case these kind of fiber you cannot use, because they are, one thing, they are bulky if you are going to use the high power fiber laser, and the thermal management is really a big issue. I'm not saying that they are not used, they are useful, they're still used and for the application, but there are certain applications like if you want to give you fiber laser to for the defense application for the army, so there they cannot use the carbon dioxide laser. Okay, so whenever you want to use the kind of the transportation, or you want that your system should be compact, and you want to make the laser up to that particular level, then you go for uh, then you look for some substitute. So what is the substitute? One of the substitute is suggested that why you are not looking for a fiber laser. After the invention of the fiber, in around I think 1960 or 1964 only, they have also in the meantime in some 1960 there are so many inventions has been done. In case of I think in year 1966, fiber amplifier has been designed. So they said that if you use a fiber as a host material, and you try to design a fiber laser or waveguide laser, that can be really handy for you. And because they are not bulky, one of the advantages, they are not bulky, they are light in weight. And if somehow you are able to go up to the power level which is there, or you even close to that, it will be really helpful for the application where you want to move your fiber from one place to another place. And the second advantage is the fiber is having long range. Okay, long range fiber you can easily use. You can use a kilometer fiber. You just pull out its at right radius, and you can get a fiber so of even 1,000 kilometers. So that what it will do, you gain medium, you can actually, by using this, you can actually increase a long gain medium, which is not there possible in case of CW laser or that laser. So even your gain median can be order of kilometer or meters, whatever you require. So your power level, you can get a large signal gain in that particular case. So fiber use करने का one of the advantages, you can get a very large signal gain. The second property is this, the rare earth doped material, which basically you dope in the core of the fiber if you want to make the fiber as a fiber laser or fiber amplifier to make them as a gain medium. Basically you dope with the rare earth materials like erbium or ytterbium or like that. So there is an inherent property of these materials to kill the thermo-optical problems raised by the high power, which is flowing through the fiber. The second, the biggest advantage is it is a good heat dissipator because of its large surface to active volume ratio. So these are the certain points which basically work on a good beam quality. This basically improves the beam quality of the laser. So it is suggested that if you try to make a fiber laser or waveguide lasers, that can be really helpful in order to get a very good beam quality, and that can be the laser which can be designed, that can be very light in weight, and that can be easily transferred from one place to another place. So just the same thing I have mentioned here, the lightweight and size, easy to handle, and because of this they are having huge applications in defense industry, medical application, and so on. So in order, now what you want to do, you want to make a fiber as a host or waveguide as a host in order to make a laser. So if you are making a fiber or waveguide as a host, you know that we need to discuss about the basic understanding of the waveguide. This is a typical refractive index profile of a waveguide, and this is the refractive index of the core. This is a refractive index of the cladding. Especially we say core and cladding in case of fiber. In case of waveguide, if you are talking about 1D structure, we say this is the film and this is the cover or substrate. So depending on this N1 and N2 and what is the width of this core, your fiber can or waveguide can support n number of modes. Okay, it can support n number of modes. If you want a single mode fiber, in that case your A value should be small, your N1 and N2 value should also be small. So one of the point which we can note from this slide is a fiber can support single mode or multi-mode depending on what is the N1 and N2 value you have taken, what is the core width you have taken. Now the next question comes, if you are going to use a waveguide as a host material or fiber as a host material, then we know that just from the first slide we have seen that it can be single mode or multi-mode. Which kind of fiber you're looking for? Whether if you want to make a fiber as a fiber laser, which kind of fiber is preferred? Whether it should be single mode or it should be a multi-mode. That answer you can see it from here. If you just look at the output of a single mode fiber, it is very clean output. Very clean output, Gaussian curve. However, if you just look at the output of a multi-mode fiber, it is a clumsy output because you will see the superposition of number of the modes, the fundamental mode and higher order modes. So whenever you are looking for a very good beam quality, you want very good precision, in that case it is always recommended that you should use a single mode fiber. But at the same time, I would like to mention that it is not that you cannot use the multi-mode fiber for the designing of the hyper lasers. Wherever you are not very much concerned about the very fine beam quality, even the few mode fiber you can use. But one of the takeaway from this slide is your fiber should be single moded if you want to make this fiber for the use of the fiber laser. Now come to the other condition. What is the condition for the fiber to be single mode? That you need, since you need to maintain that, you should know about it. Okay, what is that condition? If you look at the fiber, we already know that there is a parameter, very important parameter, which is called V parameter. This V parameter should be less than 2.4048. And if you're talking about the optical fiber, And if you're talking about the planar waveguide, it should be less than 3.14. And if you look at the V parameter, what is the V parameter? It is having K0, it is basically 2 pi by lambda. So lambda is there. A is the core radius, N1 and N2 are the refractive indices. So for a given numerical aperture and given the just the range of the numerical aperture I have mentioned here, and the operating wavelength is say 1.55, your A can be in the range of 5 to 10 micron. Or for the planar waveguide, the A should be less than the 3 micrometer. This I'm saying this indicates what is the numerical aperture, and because you see it depends on number of parameters, okay, other parameters. So if the other parameters are like that, your A should be less than 3 micron, and here A should be less than 5 to 10 micron. So what is the point which we can note it from here is, for the single mode propagation, your core size should be small. Means there is a limitation. There is a limitation that you cannot increase the core size beyond this for a given other parameters like numerical aperture and operating wavelength. So this is about a single mode fiber. Now what it will do, since you cannot increase a core size up to say this is the maximum allowed the core size, actually it is giving you a power limit which can pass through it, because it is a fiber. So there will be some damage threshold for it. So since your core area is fixed, core radius is fixed, so core area is fixed, okay, and that should be small. You cannot go beyond this. It means basically it is giving you P threshold. There is a P threshold. There is a threshold power which you cannot flow through this optical fiber in order to make this fiber safe, in order to avoid the damage in the fiber. This is one thing. The second thing, even before this threshold power, since the area is very small, the intensity, we know that intensity is P by A. Since the area is very small, what it will do, the intensity of the incident light will be, the intensity of the incident light will be very high. And what it can do, it can basically create some non-linear effects, which is not required for the application which you are looking for. What it can do, if it just in the first few slides we have seen that it can look for the the frequency generation. Means you have a signal wavelength and you have a pump wavelength, both are propagating, and if even you are below the threshold but your limit is in the non-linear effect limit, then it will also create omega s plus omega p. It will create omega s minus omega p, which is not required right now. This is not required for this 5 laser application. So this is the problem with this small core. Now the question comes. You said that you want to make a fiber laser. For the fiber laser, the fiber should be single moded, but the single moded small core is there. So there is a threshold limit. And if there is a threshold limit, it means there is a threshold limit on the output power of the fiber laser. So we cannot go beyond that. So the question is, then how you can increase the power level of the fiber laser? So the answer is simple. You can come up with certain design which can give you the large core, even with single mode. If that is possible, then of course you can increase it. Otherwise, there is no way. If you want to increase the power, you have to increase the core area. Okay, so if there is a possibility that you can increase the core area, all right, ensuring that this provides you the single mode operation, that will help you in increase. That will basically help you in order to increase the power level. And in recent time, whatever the article you will read about the fiber lasers, you will see that they are talking about the LMA fibers, the large mode area fiber. So the large mode area fibers, of course, there are, I'm not saying that this is the only the parameter which is required for the increasing the power level. There's so many things about, like what kind of pump source you are using, what about the repetition rate, and so many things are there. But one of the key feature is about your LMA fiber. So LMA fibers are fiber which gives you the large single mode operation even with a large core. So here I've just pointed out few of them. There are a number of ways of doing it. So a few of them I have mentioned it. One thing is by controlling the index difference between core and cladding. So you know that normally this is the say this is your refractive index profile, this is your N1, and this is your N2, and this is your A. And you know that what is the range for the single mode operation, 2.4048, and this V is 2 pi by lambda A, n1 square minus n2 square raised to power 1 by 2 should be less than 2.4048. So what you can do, here A you have. So what you can do, since your this product should be less than 2.4048. So one idea is you reduce this n1 minus n2 and increase A such that it always remain in this range only. So you, instead of taking this, you can design this kind of fiber. This is your N1, this is your N2, and this is your A. Okay, so ensure that you are increasing the A by decreasing the difference between N1 and N2 such that this limit is there. But the problem with this kind of fiber is, since N1 minus N2 is very small, this fiber will be very sensitive to the bending. So this is of course one of the way and has been used to increase the power level. Now the second way is you tailor the refractive index of the profile inside the core. So this is the conventional fiber. You don't change this N1 and N2, but instead of writing this step index score, you try to use a graded index score like this. So instead of using this, you use a graded index score like this, N1 and N2. And if you look at the analysis of the graded index score, there you'll see that the cutoff range is not 2.4048. It will be more than this. So still it will give you, the large mode related to the conventional fiber. But the only problem is now your the output will not be exactly Gaussian, slightly away from the Gaussian. So it will be not exactly Gaussian, it will be something like this. In between there will be some dip. So, but of course this is the another way of doing it. The last point I mentioned about the photonic crystal fiber, which is a specialty fiber. I'll discuss in detail about this. But the one of the ways can we design certain fiber which is not going for even the specialty optical fiber using the well-known the MCVD techniques. Can we design any fiber on that? So what we have done in the past few years, what we have designed a leaky fiber. We have taken a concept of a leaky fiber. What are the leaky fiber? I'll discuss in detail after a few slides. So I think I have to be quick now because we have limited time. So the leaky fiber, what we have done, we said that okay, you have a core and you have a cladding, and you want to increase this. Okay, don't worry, you increase it and let supports instead of one mode, let's support this is n number of modes. But you increase the core area, but at the same time you also do some modification in the cladding. You change the cladding in such a way, okay, the normal cladding is like this one, but you change the cladding in such a way by tailoring the refractive index profile in a cladding such that even in the radial direction or angular direction, this is the radial direction, you can see it is not a conventional this cladding. Instead of that, we are using the different kind of cladding, keeping in mind that all the modes will be leaky, keeping in mind that all the modes suffer from finite loss, and just make sure that the mode which you want that it should retain, which is a fundamental mode, should go for a very nominal loss, and and the all other modes should suffer from a very high loss. So this idea we have used, and what happened in this idea, if there is a fiber, you launch a light, initially there will be 4 or 5 modes here, there will be 4 or 5, just for the sake of this I'm saying 4 or 5 modes are here, and after a propagation length of certain distance, say L, all these, since the higher order modes are suffering from a high loss, after a certain propagation distance, all will be filtered out, and you are basically left with the fundamental mode. So this is called the idea of mode filtering, and this mode filtering we have used in order to design the various fiber designs. So what we have done, we have designed we have changed the waveguide design into 1D structure, 2D structure, fiber structures, and photonic crystal fiber. So this is the, I think, the ray theory. Quickly I move towards this. The light guidance in the fiber is won by the ray theory. We already know that the process of total internal reflection. Okay, this is the give the the rough idea how the light propagates through the fiber. But the actual one is the wave theory, in which you write down the the Maxwell equation and solve it, and then you see that the what are the modes. Modes are basically the field pattern. Modes are basically the field pattern which propagates along the length of the fiber or waveguide without changing its shape. So you have, if you have a refractive index profile like this, it will give you certain solutions, and these are called the different modes. And each solution have different, a unique the field profile. Just like if you want to compare it, compare this with the particle in box problem, you can easily compare it. So this is about the mode theory. So waveguide theory and waveguide theory, and the output of this waveguide theory is once n1 and n2 is given, and you apply this, you find out the certain solutions. So this is the modal analysis I'm talking about. I don't know, someone is writing here. Okay, so this is the typical the equation I have written over here, which you, when you write down the Maxwell equation, apply the boundary condition, you get this kind of second order differential equation. And depending on what geometry you are using, whether you're using a waveguide or fiber, you find out the modes as a solution. TE and TE modes, you will get the solution in case of the planar waveguide. So you'll find out this kind of refractive index profile. This is the refractive index profile, and this is the the mode field profile of the fundamental mode. So I'm just trying to explain what is the guided mode. So in case of the guided mode, this is a refractive index profile. The guided mode will be like this, in which in the high index region you have a oscillatory solution, and in the cladding region you have decaying solution. So you can, from here you can see that the most of the power will be inside the core. However, there will be a nominal power in the cladding region, and this is also useful. Power in the cladding region also used for the sensing. The number of the, I think, lectures you already have on the sensor. So one of the application of the sensor is because of this the power which is there in the cladding. But this is about the guided mode. Now the question comes, if I add a layer over here, this is a guided mode. If I add a layer in the the cladding region somewhere here, what will happen? The layer, see, the light, the intensity was going down inside the cladding region, but if I'll add a high index layer over here, again we'll get the oscillatory solution. You see, here you have a high index layer, you have an oscillatory solution, low index layer, you have a decaying solution. Now, if you add a high index layer, you'll get a oscillatory solutions over here. So this is called a leaky mode. Whenever you have a high index cladding, in the cladding region, a finite power will actually go inside the cladding region, and that is why it is called a leaky mode. In our structure, what we have done, okay, let us increase the core size, and let the n number of modes should come into this. Okay, and now what we'll do, suppose we'll add a high index layer of this, not exactly this one, high layer index of up to this point. These modes are having the refractive index indices smaller than this one, so these modes will be leaky. Now if I increase the the refractive index of the cladding up to this point, now all these modes are having the refractive index smaller than this one, but this mode is having the refractive index still larger than this one, so this won't be leaky, this mode will be guided, and all these modes will be leaky. Now if I use this kind of structure, all the modes will be leaky. Now the leakage loss, which is very important parameters in our case, leakage loss, which is very important parameter in our case, is going to depend on one thing: what is the mode you are talking about, what's its refractive index, or what's its effective index, and at which distance you are looking this high index region. If this high index region is close somewhere here, the loss will be more. If this high index region is far away from this guided the guiding code, the loss will be small. Okay, so in this case, what we know that for the fundamental mode, the loss will be minimum because of the propagation constant is having the highest value. Now, what about the distance? So that advantage is always there for the fundamental mode, but we always want to further increase the loss for the higher order mode. So if you use this kind of structure, the distance will be same for all the modes. The distance for the distance of all the modes from the high index region will be almost same. So in order to get the better the difference of the loss between fundamental and higher order mode, we said that instead of using this design, what will be if you use this kind of design? If you use this kind of design, the fundamental mode which you want to be retained, it will see the high index region at certain distance somewhere here, and the next higher order mode will see the higher order mode, the high index region at at a very smaller distance comparison with the fundamental mode. So this kind of structure will create a large difference between the loss between the fundamental mode and higher order mode. So this principle basically we have used in order to give the design in case of waveguide and fiber. So I think I have 2 minute slides. I will quickly move for this. So the first slide we have given for the planar waveguide structure, and I will not go into detail of the mathematical which I've already written because I think we have half an hour time only. So this was the first design we have given for the planar structure, not for the fiber structure. We said that you take a substrate which is the uniform substrate. Core is also the same. You take a large core which is a uniform. Okay. Now instead of the uniform this kind of cladding, you take a graded cladding. Take this kind of graded cladding whose profile will defined by this refractive index profile. And if this is kind of structure, you will see that this will ensure a high difference loss between the fundamental mode and higher order mode, and it will be going to show you the effective single mode operation. We don't say it is single mode operation, it is an effective single mode operation because it shows the single mode operation after certain propagation length. So in order to solve this, we have used the transfer matrix method, which I'm not going to discuss right now because we don't have enough time. But you can use the transfer matrix method developed by one of the speakers. Just to have listen. I think the morning session, Professor Noy, Professor Gata. So if you use this kind of mathematical structure and you try to solve it, you'll find out the solutions of the losses, and results are summarized over here. See what we have done. First, we have tried to see what is there any difference? Is there any effect of this profile parameter, structural parameter on the cladding Q on the BR, which is a real part of the propagation constant? You can say this is the effective index of the modes. You can see here the refractive, the N effective is not going to change with this Q value, which is good because the dispersion property of the new design and the normal cladding structure both are same. So we are not worried about some new effects, which is unwanted effect. So this is, we have checked it for the various values of the V parameters and the various values of B by A parameters, and even for the various designs like symmetrical waveguide and the anti-symmetric waveguide. Then we have seen the effect of this Q profile on this loss. From here you can see that as we are changing the Q value, the loss of the modes are increasing. This is the first point. The second point, the loss of the first higher order mode is much greater than of the fundamental modes. The loss of the fundamental mode which you should keep, it is much lower than the first higher order mode. We are not calculating the rest higher order mode because the loss of the rest higher order mode is even greater than this fundamental mode. So if you are able to show that this mode will be filtered out, all the rest will be filtered out. So one thing we have seen then that Q profile is having the impact on the loss, and the second thing is the differential leakage loss between this is good enough. Now the next we have seen the effect of this V parameters. We have done it for the 6, 8 and 10, and we have got the obvious result that when you increase the V value, basically V value increasing means you are giving tight confinement to the light inside the core. So most of the power will be there in the core. So of course small power will go to the cladding, so the loss will be small. Next, we have shown the effect of, the effect of this B by A parameter. What is B by A parameter? B by A parameter means this is your A and this is your B. So B by A, small b by A means a very steep profile, large B by A means this kind of profile. So it is very much clear from here. If you take large B by A, the loss will be small. For the large B by A3, the just look at the loss, it is small. So whatever the expected result that we have get, but the another the point which you can note it from here, all these design parameter is given you. If you here, the differential leakage loss is almost same in the entire range. If you want to change the differential leakage loss and absolute leakage loss, you can tune it by using the B by A value. So if you B by A you increase, it will basically increase the differential leakage loss for a given B, any for given Q value. If B by A is changed, here see the differential leakage loss is this one, and here it is this one. So if you are designing some waveguide and you are seeing that you need to change the differential leakage loss, you know that the idea is just tune the B by A value. So we have done certain calculations, and based on this certain calculation, you can say that this kind of structure is able to show you the effective single mode operation with a 4 millimeter propagation distance only. And the size which we are getting here, it is almost 2.25 times greater, larger than the conventional structure size. Bending calculation we have also done. So, and we have seen that we have tried to find out the bending radius, which is beyond which there is a the bending loss is insensitive. So we have find it out. It is a 3 centimeter bending radius. Not going into detail. So you always need to come up with the simplified design. So which can be fabricated. So we have also given a simplified design. Instead of giving the graded index, we have given this kind of step structure, and for this step structure we have also shown that if you can get the similar kind of loss profile to get the better result. Okay, so this is about the planar waveguide. Then we have again given the another structure of the planar waveguide, in which instead of having gradually this, what we have done, we have given the high and low index, where the high index is having the same refractive index. However, the low index region is basically tailoring, and it is governed by again a Q profile. So Q profile will be linearly varying, and it is varying like this for different values of Q. So when we have given this structure, why we have given this structure? Because we know that experimentally it is always possible to fabricate low and high index region instead of graded index. So we have given this kind of design. However, we have changed this the value of low index region, and it is governed by a Q value. Why we have done this? Because if you don't get if you just randomly you try to do something, it will not give you the idea, because you have to analyze. If you are doing theory, you have to analyze all the parameters in detail. So after giving this kind of design, we get a result, and it was initially it was really disturbing result, because whatever expected, that we are not getting. The expected thing is this one. The expected thing is this one. The lowest loss is for the fundamental mode. Then you have the loss of the next higher order mode, and then you have a loss of the next higher order mode. When I tried to do this, what I have seen that initially the same trend what follows, but then this loss was crossing the next higher order mode of the loss. So this was initially it was disturbing why this is happening, but then when we have realized it, we have find out it is because of a special effect of the physics, which is called resonance. And because of this resonance, this has given a new idea. This has actually given a new idea to come up with some new design. So this has actually solved our problem. So if you we have after analyzing, we have find it out. If you take Q is equal to 1, that will give you very high loss to the higher order mode of 10 dB per mm, and just 2 mm length of fiber can filter out all the modes, and your core size will be almost 3 times larger than the known one. But one thing is, it has given you the idea about the how much fiber, how much waveguide length you can use for the single mode operation. But beyond that, it has given us a new idea to design a fiber, and we have used it in the fiber design. That also after some time. So this is the again the effect of other parameters. Effect of other parameters, like if you are designing it, you have to see the effect of other parameters. So we have seen the effect of B by pitch, and you see that B by pitch, it will keep on decreasing the value of fundamental mode. But in case of the first order mode, there is some ripples, and this ripples is again the confirmation that there is a resonance. There is a resonance phenomena in case of the loss of the first higher order mode. And you have done it for the different values of B by A, but practically it is not possible to go beyond this limit of B by A is equal to this value 5. So for that, you see, because of the resonance, now the loss of the fundamental is very, very small, 0.0002, and the loss of the first higher order mode is the difference is the 10 raised to power 4. So differential leakage loss is very huge here. Then again, we have seen the effect of other parameter, and it is up to the mark which was expected, and all the design parameters are given again. The same thing here. Here you have a absolute losses. You see the difference of the loss is almost flat. But if you want to change this differential leakage loss, that you can do by changing the pitch value. See, if you're comparing for the 2.3, 3.5 and 4.5 here, it will increase basically the differential leakage loss. So all these calculations basically helps the designer to to come up with a better result up to the requirement of the experimentalist. Here we have shown the field profile of the fundamental mode and the first higher order mode. Here you can see that the huge oscillations is there in case of the first order mode. However, there is some oscillation also for the fundamental mode because both are lossy. And here we have shown the contour plot of the well confined fundamental mode inside the core region. And again, bending analysis we have done, and we have found out the same result. 3 centimeter bending is there. Again, we have given this simplified design. Now we came across the idea of the resonance Waveguide structure. So what we have done, we have started the value of this, the lower index region. We have started varying from N2. We have started varying from N2, and we have tried to increase up to this, and see when we have changed this value from N2 to, and we have tried to move towards N1, we found out that for a given value of this N3, when we have changed this from here to here, we find out for a given value of N3, there is a huge loss in the fundamental mode. There is a huge loss in the fundamental mode, and that N3 we have find it out, and based on that, we seen that the fundamental mode loss is just 0.39, and the higher order mode loss is something close to 20 dB. So the simplest design we have given with a large core of size of almost 10 micron. And again, for this structure also we have done the bending analysis. So one of the key result for this one was, if you bit careful about the result you are getting, sometimes you get very interesting result, and if you analyze it beautifully, it will help you to come up with some new designs, and which may even simplify your design. So we came across this resonance coupling. So I think we don't have much time, half an hour time, so I'll skip this the 2D structure. So in the 2D structure, we have also given the large mode area designs. And one of the, before I skip this one, I'll just like to mention about this 2D structure, that it also it basically gives you the single mode operation not at a single wavelength, but the range of the wavelength. Because of the spatial structure, it gives you the wavelength range of 750 to 1600 nanometer. This kind of behavior is called extended single mode operation, which is there, especially you find out in case of the photonic crystal fiber because of the spatial geometry of the cladding. There you see, but here because the spatial cladding design, you also see the single mode operation in the range of the wavelength. So you are not restricted for a particular wavelength only. In the range of the wavelength, you will find out the extended single mode operation. This is the model field profile of the fundamental mode. You can see in the 2D case, even the field is well confined inside the core region, and this is the first higher order mode. You see the lot of ripples you can see in the cladding regions. This is the contour plot of the fundamental mode, and the area was 5 times larger than the conventional structure. These are the typical result. We have shown the typical result. We have just shown here that your waveguide, channel waveguide can give you single mode operation with almost 1.2 mm length, because it ensures the loss of very huge loss, close to 20 dB to the first mode. Again, we always give a simplified design, so that we have also given a simplified design, and that design was also able to show the single mode operations. So conclusion is, whatever the design we have given, it is not very much sensitive to the parameters. Like they are within the accuracy, within the accuracy of the experimentalist, and you have a flexibility with the parameters. So whenever any experimentalist is willing to design these parameters, so they can they see, based on this analysis what we have already done, they can tailor their design. So this is again the channel waveguide. So I will leave this because I quickly want to come to the fiber structure. Okay, multi-clad fiber structure. This is the structure we have given in case of the fiber, where we have taken the uniform core and the leaky cladding. And again, the leaky cladding is having two parts. One is the the low index region. This is the low index region. The low index region refractive index changes, and it basically follows the power law profile given over here. This power law profile, and there is a high index region. These are the high index region. These are the high index regions. So we have this is the low index region or low index region, and these are the high index region. So low index region will give you the confinement, and high index region will give you the loss. Okay, so we have tried to analyze the structure with the Q profile, and here you will see that you will see the difference. You see the difference is even in the order of 3. Means the loss of the first mode, the first higher order mode and fundamental mode is very large. It is something about 10⁻⁴. So we have also seen the effect of the B by A parameters, and from here we have analyzed that if you want to increase the differential leakage loss, it is always better to tune this, the B by lambda parameter. We have also seen the effect of other parameters like D by pitch, and it is quite obvious that if you increase the D is what? D is basically the width of the low index region. So if you increase the width of low index region, means confinement you are giving, so of course the absolute loss will keep on decreasing. And after that, we have seen the effect of the numerical aperture, and this is also quite obvious. Just I think in the beginning I have mentioned that if you increase this N1 minus N2, if you decrease this N1 minus N2, it will be your bending sensitive. Okay. Similarly here, if you increase this difference, the loss will decrease. It means it will be even less sensitive to the bending also. We have also seen the spectral variation of this structure, and this structure also shows you, this kind of behavior, single mode operation, not only single wavelength, but in the range of wavelength from 1.45 somewhere here to 1.47, because the maximum loss of the fundamental mode is here, which is even less than 0.1 dB, and the minimum loss of the LP11 mode is also something close to here, which is 1.45 here. It is close to, I think, 5 dB. This is the field profile we have plotted for the fundamental mode, and which is showing the well-confined region. And these are typical results we have shown. So you'll find out the area which is very large area, something around 706 micrometer kind of. So in order to explain the principle, whatever the principle I have explained, that was just based on the simulation. In order to verify this, what we have done, we have a collaboration with the University of Nice. So that time we have given our design to our collaborator. This design we have done, we have made this kind of structure, which is very simple structure, and said that if you try to make this kind of refractive index profile, then as per our calculation, theoretical calculation, the loss of the LP01 mode will be 0.35 and LP11 mode may be something around 8 dB. So 20 dB loss will be something around in 3 meter. So what was our conclusion? If you make a fiber, which will make a fiber with this kind of structure, that fiber will be able to give you the single mode operation after 3 meter of propagation length. So the group has fabricated this fiber. So this is the refractive index of the profile fiber they have fabricated. And see, after doing this, they have shown the output. They have fabricated the fiber and they have shown the output after 1 meter length. See, after 1 meter length, you see the output. You know, this it will basically show you the superposition of number of modes. So there are a number of modes propagating through the fiber. Now, after 2 meter propagation length, you see the output. Some of the modes has been filtered out, so the relatively better, you know, you will see here. And after 3 meter propagation length, this is the experimental result I'm talking about, not the theoretical one. So our expectation was, if you fabricate this design and you use a fiber length of 3 meter, you get a single mode propagation, and same verification we will get from the experimental result. The comparison we have made with the theoretical and experimental, the intensity curve. This is the typical intensity curve of a single mode profile. So it is giving you small mode area, and this is, you know, this was the intensity curve of the experimental curve, and this is for the theoretical curve. So there is good agreement between theoretical and experimental, the observation we got. And then we have compared the loss as well. So you'll see the straight line. The straight line is the calculated result of the loss of the fundamental mode, and these data points are the basically the experimental the loss which has been calculated experimentally. So you find good agreement between the even the loss which we have calculated not for a single wavelength, but it is for a range of wavelength. So the result we have seen earlier, it was for a given wavelength. We have changed the fiber length and seen the profile mode filtering. So the mode filtering principle is also very much obvious, but the loss value we have also seen it is very close, good agreement with the theoretical one. So this is one of the idea that you can design a fiber which can give you the single mode operation with a very large core, and that can be useful for designing the fiber lasers where you want to increase the power level. So now the next design we have given about the leaky fiber, dual core leaky fiber, and this was basically based on the idea. This was basically based on the idea of the resonant you know, the effect which we have observed in the case of the planar waveguide. So what we have seen that if you simply tune the value of this layer, vary from the lower to higher value, at certain point of time, you will see that the effective index of the first higher order mode is matching with the mode supported in this guided structure. So for that particular point, there is a huge transfer of power. There is a resonance coupling between the inner core mode and this outer clad mode, and this ensures the the transfer of quick transfer of power from the core to cladding. So we have just encased that that concept, and what it has done, it has basically benefited us, because in this case we need not to worry about the different profile parameters, all that. We just need to use one inner core, and in the cladding we have one and two low index and two high index. Just a simplest design which is good for any experimentalist to design this kind of structure. So the observation of this spatial effect has given us a simplest design. See here what we have done. First, we have changed the value of N3 from a starting range to a maximum from N2 to N1. And if you see, initially the loss of the fundamental mode is very small, and for a given structure here, you see the loss of fundamental modes is the lowest one. Then it comes to the next higher order mode, then it comes to the next higher order mode. But if you keep on increasing the value of N3, there is a crossing point. There is a crossing point beyond which the loss of the fundamental mode will be this one. After that, the loss of the fundamental mode, the first higher order mode will not be there. The loss of the next higher order mode is having the value, and after that, the value of the next higher order mode will come. So sequence is changed, and this is because we have ensured a resonance cladding, a resonance effect in the case of LP11. So this has given given us the simplified design, and as well as it has given us the idea to filter all the unwanted mode in a very small propagation length. We have seen the effect of various the parameters like D1 parameters, and when we increase the D1 parameters due to the better confinement, because the D1 is the width of the low index region, of course the loss will decrease. So that is decreasing here. Then we have seen the effect of a parameter D3, which is basically the parameter of high index region. So you will see the loss. D3 is not the high index. Let me tell you. D3 is the low index region of the outer cladding. And what we have seen that because of changing this the D3 parameter, the loss of this fundamental mode was keep on decreasing, because of course you are decreasing the the low index width. But there is a crossing. There is a crossing of in the leakage loss of the two modes we have observed here, and this is again one of the signature of the resonance effect. And these crossing points actually helps us to give a good the design which can be easily fabricated, can be easily designed with the experimentalists. See this point and this point. At this particular point, if you see this particular point, D3 is equal to 2.4. Of course, the loss of the next higher mode is very large. That is good, but at the same time, the loss of the fundamental mode which you want to retain is also very high, 5 dB. So this is not acceptable. Okay. Now coming back to this point, you see the loss of the this mode is not so much high, but even very good. It's 55 dB per meter. It means even you don't need a meter length of fiber. Just in 36, almost less than half meter of fiber can solve your problem. It can show you single mode operation, and at the same time the loss of the fundamental mode is small, which is 0.04 dB. We have utilized this structure, and we have also seen the spectral variation of the loss. Again, you see the crossing of the curve in the LP01 and LP11 mode. This is again the signature of the resonance effect which we have tried to utilize. So now I think only 7 minutes. So the modal field pattern we have seen. See the fundamental mode is well confined, and then we have some the higher order mode which is showing large ripples, signature of the large loss in the fundamental higher order mode. This is well confined fundamental mode. Just shown you one result here that just almost length less than half meter fiber can show you the the single mode operation. So if you use this kind of fiber as a host while designing a fiber laser, that can actually enhance the power area, the power region. I think something 3 to 4 times. Now this is not about the fiber lasers, but the same idea, which is resonance effect, we have used to find out we have used in the another application which is called gain flattening. If you want to use your amplifier for the DWDM application or WDM applications, you always want the amplification and you want the amplification at the same level. But if you look at the gain curve, it is not flat. So there's so much efforts has been done to make the flattened curve. So in order to get the flattened curve, the idea is you can flatten it with the whatever the slope of gain is there. If you'll get the same almost loss curve, you can get the flat curve. So we know in case of resonance there is a sharp change in the the loss curve. So we have utilized this design. Quickly I will tell you with a small core region, we have changed the values of N3 and we have tried to find out the suitable loss curve. And we have tried to find out the suitable loss curve, and finally you'll get the loss curve which is giving you the flattened the gain, which is having the almost 22 dB gain. So the basic principle can basically helps you in designing the fibers as well. So here we'll see almost 46 modes will support whatever the design we have taken. If you take the conventional fiber N1, N2 and the core region, it will support 46 fiber, but here because of the spaces mode filtering, you get a fundamental mode even with the length of 0.40 micron. And after that, a lot of work is nowadays is doing in the case of by using the specialty optical fiber, which is also called photonic crystal fiber, which is having two types. One is step index guided, and one is the band gap guidance. In case of step index, you have a solid core. In case of the band gap, you have the hollow core, and in the cladding region, you have a periodic arrangement of the air holes or rods, which is running through entire length of the fiber, through the entire length of the fiber. So this is PCF nowadays from last few years, you can say, is they are creating they are basically the number of researchers are trying to basically working this on the photonic crystal fiber because it is having there's so many degree of freedom. There's so many design parameters. One is either you're going for a solid core or band gap. Even in a given design, the solid core, you have what kind of geometry you are using, whether it is a hexagonal, it is a rectangular, it is a triangular, and whatever the shape you are using, whether it is a circular, it is a elliptical, or maybe in first ring you have a circular, in the second ring you have elliptical, or different size of holes. So all that kind of what is the pitch value, these design parameters have so many degree of freedoms which increase its the application. And you have mentioned few of the design. This is the design is given for the dispersion compensating fiber. This is for the low band fiber. This is highly bioluminescent fiber. This is one of the design is given for the element fiber. So there are so many things. The conventional fiber cannot be achieved, can be achieved by this photonic crystal fiber. So I will not go into detail of the what kind of calculation we have done, but of course we have also used this photonic crystal fiber to increase the area. And in some of the results, you'll see that you'll find out the area which is close to 2000 micrometers square, which is much larger than whatever we have just discussed few minutes before. But only one point about the PCF structure is, the method of the fabrication process is there, but the number of the holes and all this we have to use. So the design point of view, you have to very careful in that case. But in case of MCVD, it is a well established structure. So these are the different designs we have given even in the PCF. So this is all about, you can say, the contribution we have given in case of designing your fiber, a waveguide, or 2D waveguide in order to increase the power level host, in order to make the host which can actually increase the power level of the host material by increasing the supporting the large node area design. So I think my time is up, and thank you once again to all the organizers and the faculty members, PhD students, for attending this talk. And the session is open for the question. If you have any query, you are most welcome. This is all from my side.
Thank you very much.
Any question?
Just in the time I am allowing to unmute.
Okay.
Dear participants, if you have questions, you can raise your hands, or else you can unmute yourself and ask the question to sir.
I think it's a lunchtime, so everybody.
Yes. No.
Okay. So, sir, if you have any questions.
Lalita Deshmukh ma'am, please ask your question.
First of all, I will congratulate you, sir, for such a wonderful explanation. And thank you very much, sir, for such a thorough information about starting from the basics of laser and the application belonging to the optical fiber. My question that is belonging to the excimer laser, sir.
Just a minute.
Hello.
Yes, yes,
Yes, yes, please go ahead.
please.
Actually, my question is, in case of the gas type of a laser, whether that is belonging to the neutral gas type of a laser or a molecule, and in that type of a gases, there is a particular proportion or in terms of a pressure, the insertion with regards to the active center that will be mentioned, sir. But with regards to the excimer laser, why the continuous supply of active centers or active gases is required? This is my question, sir.
Question is not very much clear because there is some problem with the audio problem. So can you repeat the question about the excimer laser?
Yes, sir. About the examiner laser. My question is belonging to, am I audible now?
There's some breaking in the voice. There is some breaking in the voice. So
Right.
examiner laser I just heard. So what you can do, otherwise you can write a mail to me because you are writing something about examiner laser, but I'm not
Yes.
able to hear it properly. So what you can write a mail to me. My ID is ajeetdph@dtu.ac.in, and then I can reply
Okay.
because
Okay, sir.
somehow I
Thank
don't
you.
know what is the problem. Hello, because I'm able to hear Dr. Abhijit, but
Yes, yes.
your voice is maybe some internet issue.
Wait, sir. I will use my headphone. Hello, am I audible now?
Yeah,
Yes,
yeah.
ma'am.
Okay.
Okay. My question is, sir, with regards to the gas type of a lasers, it may be say belonging to the neutral atom type of a laser or a molecular type of a laser. There will be a certain amount of proportionality with regards to the active center insertion is there. But
Yeah.
with regards to the excimer laser, why there is a continuous flow of active gases is required? This is my question, sir.
Why there is a continuous flow of active lasers is required?
Yes. Continuous flow of active centers. That means active gases. That is nothing but what say as a rare gas atoms or the some halogen atom supply. Why there is continuous flow is required, sir? This is my question.
So I think for this I think I have to look into that, and then I can get back to you.
Ma'am,
So
Okay.
you write an email to sir,
you write an
detailed
email to
email.
me. You write an
I will
email
share
to
you
me.
email ID.
I've already
Okay.
given my email ID. It's ajeetdph@dtu.ac.in. So I'll go
Yes.
into
Oh,
that, and I will try to answer your question.
oh, okay. And my second question is, what should be the sustainable power to work with regards to the optical fibers, sir, communication?
Yeah, you are talking about the communication, or you are talking about the fiber laser?
No, I'm talking about the communication.
So communication, it should be
Laser power. Yes.
yeah. So if you want to use just for the communication, your power level in the even in the range of few watts, like 10 watts, that is all right.
Okay.
But even your fiber can support the even I have already mentioned that because of the better the surface and volume ratio, even it can
Mhm.
support the power up to the kilowatt range. So if you
Oh,
even I mentioned about the DRDO, they have even developed the fiber of 2 kilowatt the CW layer. They have already developed it, and it is
oh,
working fine.
okay. Okay.
Okay,
Thank you,
Thank
sir.
you, ma'am.
Okay.
thank you.
Can
Bharti ma'am,
please
ask you a
repeat
question.
your email, ma'am? Email, sir. Sorry.
My email is ajeetdph AJEET Ajeet, and
Yes.
D is the department, first alphabet of D, and PH the first two alphabets of the physics. Ajeet DPH @dtu.ac.in.
Okay.
Okay,
Thank you, sir.
okay, thank you.
Bharti ma'am, ask you a question.
Sir, in case of fiber optics related to index change,
Ma'am,
we are mentioning delta
Your
value
audio
as
is
N1
not.
minus N2 upon N1. Then, uh,
Ma'am, your voice is not audible
voice
clearly.
is not
okay, एक माझा हेडफोन कुठे आहे का
No, she's not audible at all.
No, she's searching for a headphone.
Okay. Otherwise, she can also write the mail. She can write the mail. I will.
Hello.
I will share your email ID, sir. Ma'am,
Yeah,
ask
you
you.
can share the email with all the participants.
Hello.
Yes, ma'am.
Sir, see, if my voice is reaching, then please answer.
Okay.
Otherwise, I will send you a mail.
Okay.
My question is that in case of fiber optics, we are mentioning the delta value, that is fractional refractive index change as N1 minus N2 upon N1. Then I have read that there is concept of minus delta also. So what is that minus of delta? It means
Minus.
that
Okay.
huh.
Just a minute. Let me. I can write it here. Maybe I can write it here also. See the
Okay,
delta you write about this n1 square minus n2 square divided by 2 n1 square. The concept of delta lambda they talk about sometimes they are designing this kind of fiber. Instead of designing this kind of fiber, they design in the between they design this, and then they go for this kind of trench kind of structure. So in order to design such type for trench kind of structure, they instead of writing this delta, they use this minus delta. So whenever you have trench like this, they somewhere they'll write this is a delta. Say this is they are writing this is a delta, and this they will mention minus delta. So this is kind of only the nomenclature difference.
Okay, sir. Okay.
Nothing.
Thank you, sir.
Nothing special in that. That's the only thing nomenclature they use.
Okay, sir.
Okay,
Thank
up
you,
and
sir.
down. This up and down.
Okay. Okay, sir. Thank you, sir.
Thank you, ma'am. If there are no more questions, then I would like to thank Dr. Ajeet Kumar sir. Despite his very busy schedule, he has agreed to deliver a talk in the Atal Academy sponsored faculty development program on photonics, active learning in optics and photonics, organized by Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur. Sir has taken, as Lalita ma'am already pointed out, he has started from basics of optical fiber, basics of light, and covered a lot of things to the application of optical fiber, design of optical fiber for as a waveguide for application in the high power lasers. Sir has covered almost every aspect regarding this designing and application, and given a wonderful, thought-provoking and inspirational lecture. I, on the behalf of myself, on the behalf of my institute, Department of Physics, Electronics and Photonics, Rajarshi Shahu Mahavidyalaya, Latur, and on the behalf of participants, I sincerely thank Dr. Ajeet Kumar sir for his wonderful lecture. Thank you, sir.
Thank you, sir. I like to mention one thing. I don't know how you have arranged all this, but when I have seen this schedule which you have sent it to me,
Yes, sir.
the schedule is having 4 generations. One generation is my supervisor, Dr. Vipul Rastogi. His
Yes, sir.
supervisor, Dr. M.R. Sunoy, and the supervisor of Dr. M.R. Sunoy is Professor Ajoy Ghatak. So you have
Yes,
covered
sir.
all 4 generations.
Yes, sir. Yes, sir.
In a single platform. So
Yes.
thank you so much for inviting me for
Sir,
this. Okay, thank you,
this
sir.
could have been 3G due to your presence only. This has become 4G. Thank you, sir.
Yes, thank you. Okay.
Thank you, sir.
Okay.
Thank you, sir.
Okay, bye.
Dear participants, we are at the end of this session. You can